Thank you. And also thanks to Fernando for the kind invitation. So I would like to discuss some joint work with Pierpaolo Esposito from Rome and with Matt Gursky from Notre Dame. OK, so let me start recalling what is the determinant of the Laplacian. So I consider a very simple setting, a two-dimensional surface, compact, no boundary. Delta G is the Laplace-Beltrami operator with respect to a background metric G. And then you consider the spectrum of the Laplacian. And of course, the eigenvalues form a sequence that is diverging. The determinant of, say, minus Laplacian is defined formally as the product of all the eigenvalues. So usually physicists are happy with the formulas of this type. But yeah, as a mathematician, if you take the product of an infinite set of numbers that is diverging, then OK, you might have a problem. But there is a way actually to make sense of it, OK, via regularization. So you consider the spectral zeta function. So just take the series of the eigenvalues raised to some negative power. OK, so you have the Weil's asymptotic law, which, so I don't care about the multiplicative constant, but so the Weil's asymptotic law gives you a rate of divergence of the eigenvalues depending on their index counted with the multiplicity. So they diverge like j to the 2 over n. So therefore, if you take s to be complex valued, and if the real part is large enough, then that series is well defined. And now you do a formal computation. So you differentiate the zeta function with respect to s, and you write lambda to the minus s as e to the minus s log lambda. OK, so differentiate with respect to s. So you get this expression. And if you take s to be 0 in this formula, then you get the sum of the logs of lambda j, which is the log of formally like the log of the infinite product of the lambdas. OK, so then you define this function determinant prime to be exactly this expression. OK, in fact, this is a regular function if you take the meromorphic extension in S. OK, so why is that? OK, you can write the zeta function in this way. So the sum of lambda j to the minus s can be written in terms of an integral involving the gamma function. And you can view this operator as the trace of e to the delta t, so of the heat kernel. So basically, you apply the heat kernel on the eigenfunction phi j, and then multiply by phi j and integrate. OK, but so you can recall that the heat kernel has also a sort of local expression. OK, so if you use the representation formula for the heat kernel, that's just the trace of the heat kernel using the standard coordinates. OK. And this quantity expands, so you can do a sort of formal Taylor expansion of the heat kernel. And you see that the Gaussian curvature is involved. And therefore, the zeta function can be written in this way. Okay? So when s goes to 0, this term sort of cancels out. And therefore, the function is regular near 0. OK, so that's actually a proof of the fact that the zeta function extends smoothly near 0. So this formal expression for the determinant is actually well defined. OK, so in 2 dimensions, the Laplacian is conformally invariant. So if you rescale the metric in this way, then the Laplacian just scales pointwise inversely. And you have the following transformational law for the Gaussian curvature. So kg is the background Gaussian curvature, and kg tilde is the conformal Gaussian curvature. And so this properties allowed Polyakov in the 80s to compute the variation of the determinants with respect to the matrix with the same volume. So basically, you can compute the derivative of the conformal volume with respect to a variation of the metric conformally, and then you integrate to reach every element in the conformal class. Okay, so he proved the following formula for the difference of log of determinants. Okay, and so W is the conformal factor here. So when you write it in exponential form, and then you have this integral of the Dirichlet energy and this term involving the Gaussian curvature. So it has a role in string theory, this action, and it is related to the Moser-Tudinger-Onofre inequality. Okay, in fact, so if you consider matrix with say unit volume, then this action is maximized exactly on conformal factors of Möbius maps. So there is some conformal invariance. So for positive genus, it's quite easy to find extremals. So basically, so if you fix the volume, which is the integral of the exponential of u, the function just becomes anti-coercive and it's easy to maximize. And on the sphere, you can exploit, in fact, the Möbius action. So this was done by Aubin and Osgood, Phillips, and Sarnak with a recent sharp inequality by Guillaume Moradi-Pham. So you can use the Möbius action to sort of balance the metric. So you can imagine the sphere to be embedded in R3. And you require, so with the Möbius action, so via degree theory, you can achieve that the center of mass of the conformal volume is exactly at the origin of R3. So in this way, there is an improvement of the Moser-Tudinger inequality, which gives you actually an extremal for this action, also for the case of the sphere. Okay, so then Osgood, Phillips, and Sarnak studied the problem of isospectral metrics. Okay, so they proved that in fact, so if you consider a class of metrics with a fixed spectrum, then they're compact in any smooth sense. And they used actually the determinant to prove this property. So the case of the sphere is easier in this respect, because there is just one conformal class, so all metrics are conformally equivalent, okay, up to diffeomorphism. And since the determinant is bounded, so the determinant determines the spectrum determines the determinant, and if the spectrum is fixed, the determinant is fixed, and that gives you, by this formula, a uniform H1 bound on the conformal factor. But then you can go more precise in the expansion of the Hith kernel, so via the parametrics method, so it's a sort of formal expansion. And you find that, in fact, so the trace of the Hith kernel can be expanded in this way. So you find a sort of truncated series in T of integrals of some universal polynomials in the curvature and its derivative somehow. Okay, and so it was proved by McKean and Singer that the leading term in this expression omega j is indeed some Sobolev norm of the Gaussian curvature, which is again some Sobolev norm of the conformal factor. So if you control the spectrum, then you control all the Sobolev norms of the conformal factor. So that's how it goes on S2. For positive genus, it's actually trickier. So we saw Melanie's talk yesterday. Okay, so even if you find a nice conformal representative, so say you uniformize the Gaussian curvature, you might still have degeneracy in the Teichmüller space, so you can have a formation of necks. But somehow, so if you have a formation of neck, after rescaling, it's like having a long cylinder. And if you have a long chunk of a cylinder, you can stick in lots of slowly oscillating modes. Okay, so somehow you get many small eigenvalues for the Laplacian. And this allowed Volpert to show an upper bound on the determinant depending on the length of this neck. Okay, so if L goes to 0, then the determinant should also go to 0. But that's impossible if you consider a class of isospectral metrics. So the spectrum gives you actually a lower bound on this next size. And then once you control that, you can use a classical theorem by Mumford, which controls somehow the whole topology here. Sorry, not the topology, the Teichmuller element. Okay. In higher dimensions, actually very little is known. So this is somehow parallel to the study of extremizing fixed eigenvalues for the Laplacian on a given surface or manifolds. So there are few results by Ellis and Paul in 3 dimensions, but within a fixed conformal class, or by Zhu, but under some sort of restrictive curvature assumptions. Okay, so let me describe general operators of which the Laplacian is a particular case. So some linear operator is called conformal invariant of by degree A and B if when you change conformally the metric, it transforms covariantly in this way. So e to the 2w is again the conformal factor, that's a conformal change of the metric you're doing. Examples are, so we just saw the Laplacian in 2 dimensions. Okay, so in this case, A is equal to 0, so the Laplacian just scales inversely to the metric. It's not true for the Laplacian in higher dimensions, so you need some sort of curvature correction. So you introduce a conformal Laplacian. So you add to the Laplacian a multiple of the scalar curvature, and then it transforms nicely covariantly. Another example is the Panitz operator, so which was mentioned by Alice. So it's a 4th order operator, and it has a role in 4-dimensional conformal geometry, or conformal geometry in general. So the leading term is the Laplace squared. And then again, you have some sort of curvature corrections which make it conformally covariant. And another example is the Dirac operator in dimensions 2 and higher. Okay, so in dimension 4, in fact, Branson and Ørsted were able to extend Polyakov's formula. So they proved this very general result. So take any conformally covariant operator, so according to the previous definition. Then there are coefficients, gamma 1, 2, and 3, depending on the operator, such that so whenever you consider ratios of the determinants and you take the log, then so this expresses as a universal linear combinations with coefficients different depending on the operator of 3 universal functionals that are actually explicit. Okay, so the expressions might look a little nasty, but in the next slide I will comment on the naturality of these functionals. So I repeat, so there are 3 universal functionals such that when you consider the variation of the determinants of this operator, then this is a linear combination of 3 universal functionals with coefficients depending on the operators. Okay, so in these formulas, W is the Weyl curvature and Q is the Q curvature, which was also introduced yesterday by Alice. And yeah, it's I recall it's a sort of a conformal counterpart of the Gaussian curvature in 4D. So some comments. So the 3 functionals that I listed above are actually quite natural. In fact, if you extremize the first functional, then the norm of the Weyl tensor is constant. If you extremize the second functional, then you get constant Q curvature. And if you extremize the third functional, then the Laplacian of the scalar curvature is a constant, which means that the scalar curvature is actually a constant. So you're finding a Yamabe metric. So let me also recall that in 4 dimensions you have a Gauss-Bonnet formula involving the integral of Q and the Weyl tensor squared. So that gives you the Euler characteristic. So each term separately is not a topological invariant, but since the integral of Weyl squared is a conformal invariant, also the integral of Q is a conformal invariant. And so let me mention that, so as we saw yesterday in Alice's talk, So sometimes in conformal geometry you want to find somehow the best possible conformal representative. Of course, one natural choice is a Yamabe metric. Okay, so it's very natural, but it's not always somehow the best possible choice. Okay, so depending on the problem you're studying, well, you might find a different optimal conformal representative. And in fact, Gursky proved some rigidity results for Regularized metrics in 4 dimensions, choosing exactly as a conformal representative one extremum of a determinant functional, so not necessarily a Yamabe metric. Okay, so in the examples I described above, then you have explicit values of the constants gamma 1, gamma 2, and gamma 3. Okay, maybe they won't tell you much, but somehow something which I would like to comment on are the signs of gamma 2 and gamma 3, so which are related somehow to the principal terms in the functional determinants. So somehow if gamma 2 and gamma 3 have the same sign, then somehow the principal parts in the functional are sort of cooperating. If they are opposite signs, then it's more tricky. And so just for convention, so sometimes I will just switch the sign of all 3 constants. So somehow, because I prefer to have a functional which is coercive rather than anti-coercive, or convex rather than concave. So sometimes I will cheat on the signs. Okay, so what is known about extremizing functional determinants? There is a general result by Ellis and Paul in 1995. So they assumed that the gamma 2 and gamma 3 have actually the same sign, so they're both positive. And they also assume this condition, so it's a sort of Gauss integral bound of a Gauss-Bonnet type. I will explain. Then in this case, you can actually find an extremum for the determinant. Okay, so what are these conditions? So this condition 2, so as I already said, so having the 2 gamma i's with the same sign helps for coercivity. And this other term sort of controls the exponential term appearing, so the integral of the exponential term appearing in the functionals. In fact, you have a sort of sharp Moser-Tudinger type inequality, which was derived by Adams. And so if you control somehow the principal terms, if you control this Moser-Tudinger constant, then you have actually a nice coercive functional, and you just apply the direct methods of the calculus of variations. So the assumptions are conformal invariant because of the comment I made before, and they're roughly satisfied in positive curvature. So Gursky proved that if you are in positive Yamabe class, then there is precisely this upper bound on the integral of the Q curvature. But differently from the 2-dimensional case, so the maximal Gauss-Bonnet integral on a compact surface is when you are on the sphere. So it's either 4 pi or 0 or negative. But in 4 dimensions, the integral of Q can actually be arbitrarily large. So there are many examples, especially in negative curvature, like hyperbolic manifolds, where this integral can be actually arbitrarily large. Okay, so and it's actually open the question whether you have possibly uniqueness of these extremal metrics. There is a sort of related results by Gursky and Streets, very recent, for the sigma 2 equation, so which is in a sense similar to the Q curvature equation, but not quite the same. So somehow it's a little more rigid. And in this talk, I would like to discuss cases when either the second assumption fails, or when also the first assumption fails. And as I sort of anticipated, the failure of this condition is actually much harder. Okay, so there is one case which is kind of understood. So it's the pure functional 2. So recall that these determinant functionals are linear combinations of 3 universal functionals. And I'm just taking the second one. So critical metrics for this one have constant Q curvature. Okay, so I'm just taking a functional 2. Okay, so critical metrics satisfy this equation, which is actually analogous to the uniformization equation in 2 dimensions. So you just substitute the Gaussian curvature with the Q curvature and the Laplacian with the Panitz operator, so which is 4th order. So in this case, the result by Harris and Paul applies when the integral of Q is less than 8 pi squared. And this is actually the integral of Q curvature on S4. Okay, so in this case, if you have this upper bound, then your functional is actually coercive, and you can minimize it. But instead, if you have a larger Gauss-Bonnet integral, then you lose actually bounds on both sides for this functional. So in a sense, the Gauss-Bonnet integral beats the Moser-Tudinger constant, so you lose the lower bounds. Okay, but still, in a joint work with Jadley, so from about 10 years ago, we proved that existence provided, okay, so this Gauss-Bonnet integral can actually surpass 8 pi squared, but it should not be an integer multiple of 8 pi squared. I will try to explain why, just very briefly. So the main tool is some kind of improved Moser-Tudinger inequality, which is related to this balancing condition bioband that I mentioned before. So to balance a conformal metric on S2, it means that you need to sort of spread it macroscopically over the sphere. So somehow the more you spread the conformal volume macroscopically, the better the Moser-Tudinger inequality becomes. Okay? And this has a consequence in the variational structure of the energy, because just let me illustrate a simple case. So I'm assuming this Gauss-Bonnet integral to surpass 8 pi squared. So suppose it's between 8 pi squared and 16 pi squared. Okay, so the first other range allowed here. Okay, then I said in this case you lose lower bounds on the energy. But it turns out that you can describe very precisely what is happening if you lose these lower bounds. So if this energy becomes very large negative, then the conformal volume must concentrate near a single point of the manifold. Okay? So now suppose your manifold has some topology. Then if you move this concentration point around the manifold, maybe you can find some non-contractible cycle, and that gives you enough structure to use min-max methods. Okay, and in fact, I mean, this strategy works quite similarly, provided, I mean, for more general determinant functionals, provided the 2 principal terms have actually the same sign. But to apply min-max theory, so you need a combination of 2 ingredients. So one is topology, which I kind of just described, and the other is compactness. Okay? And this compactness condition is related to this sort of non-resonance hypothesis we have. So we require the integral of Q to be not a multiple of 8 pi squared, so the integral of Q over the sphere. So why is that? Okay, so in general, you can, so for this problem, so you can apply some monotonicity arguments by Michael to solve, so typically you have 2 alternatives. So you either find approximate solutions, so via min-max methods to your equation, or you have this alternative, so you perturb the equation and you find exact solutions. This is a little better than just Palais-Mail sequences because you have an exact solution and you have a better control. Okay, so you're able, by this method, to actually solve a perturbed equation. And then you can have your data converge to the original ones. And you try to understand whether solutions stay compact or not. Okay, so if you wish to pass to the limit, in general, you might expect loss of compactness, and then you try to reach a contradiction. So a contradiction comes, in fact, from this non-quantization assumption that we have. So if LOAP occurs, then you can use the Green's formula, so following some argument by Brezis and Merle, to show that actually the conformal volume accumulates only at finitely many points. So away from these points, the solutions, if you subtract the average, converge to a solution of this equation with the right-hand side now completely degenerate to a sum of Dirac masses. And this somehow tells you the profile of the blowing up solutions away from the blowing up points. Okay? Now, the operator on the left-hand side is linear. So the singular solution is a linear combination of Green's functions with simple poles. And the Green's function in 4D for this operator, whose principal term is the bilaplacian, is logarithmic. Okay? So just like the Green's function in 2D. All right, and then you do some bubbling analysis, and you can actually show that these quantized values are exactly equal to 8 pi squared for all blow-up points. So all conformal volume sort of reduces to a finite sum of spherical profiles, and in this way, if blow-up occurs, you get a quantization of the total volume, or of the total Q curvature. But we're assuming that the total Q curvature was not a multiple of that of the sphere. Therefore, you cannot have blow up and you have compactness. So that leads to existence. Okay, so somehow topological structure plus compactness leads to existence. And as I said, so the topological part for more general determinant functionals is actually quite similar. So the main issue is actually compactness. Okay, so I'll focus on the determinant of the Laplacian. So I call it FL. So recall that A is the conformally covariant operator. But some results actually apply to more general functionals. And I will sort of show the assumptions. Okay, so extremal metrics satisfy
Gamma 2, gamma 3 of the same sign?
Same sign, exactly, yes. So this is another ugly equation after Claudio's talk. Okay, so I don't even write it. I'll give you some idea of how it looks like. So you have some operator of mixed type in divergence form equal to some exponential of u. Okay, so to give you an idea of what this operator looks like, I just wrote, so that's the principal part in the determinant functional, depending on the conformal factor. Okay, so it's a linear combination of the integral of Laplace of u squared, and that's of that other expression, Laplace of u plus gradient squared squared. Okay, so you just write down the variation of this principal part, and that's what I call n of u. Okay, so just as a toy model, you can have in mind. So you can consider, just to have an idea, the sum of the bilaplace and the 4 Laplace of u. So 4 Laplace of u is the divergence of grad u squared mod grad u squared grad u. So these are two operators of, say, different orders, but with the same scaling properties. Okay, so if you dilate u, just considering u of lambda x, they scale in the same way. Okay. So UG is a sort of combination of the three quantities that each single term, 1, 2, and 3, is representing. So recall that critical points of 1 give you constant norm for the Weyl tensor. Critical points of 2 gives you constant Q curvature. And the critical points of 3 give you constant Laplace of R. Okay, so this quantity, which I call U curvature, is a combination, is a linear combination of the tree. So anyway, that's the equation. Okay, and the result we have is the exact counterpart of that quantization result. Okay, so again, we consider a sequence of perturbed equations, assuming we can solve them, and we have the data converging to the geometric ones. So then we consider a sequence of solutions of these perturbed equations with, so I denote by L the conformal Laplacian. Okay, so I'm taking those two special values of gamma 2 and gamma 3. So I consider a sequence of solutions of these equations with a uniformly bounded conformal volume. then you have this dichotomy. So either they stay uniformly bounded in C4 alpha, or the conformal volume quantizes as a sum of Dirac masses. Okay, same counterpart as before. Okay, so in the latter case, in particular, this constant mu, so the limit of un, must be again a multiple of 8 pi squared. So basically the same result as before. Okay, so how do we prove this result? Okay, so assume solutions are blowing up, so the supremum is going to plus infinity with n. Okay. However, some quantities still stay uniformly bounded. And you should have in mind exactly the blow-up profile, which is log x. Okay, so that just misses W22 and W14. So it is natural to expect that you get actually bounds on Sobolev norms that are weaker than W22. So you can control uniformly then. And then also, somehow following some argument by Dolzmann, Hunger-Bühler, and Müller, you can actually prove also uniform BMO bounds on these solutions. Probably you can expect a little more, but that's enough for us. Okay, so then there is also a result. So that's general for general coefficients gamma 2 and gamma 3. So unless you kill the principal part of the operator. So they proved some regularity results for critical metrics for the determinants. So they showed an epsilon regularity. So if the volume in a ball is smaller than some quantity epsilon 0, then in a half ball, you control actually the full W22 and W14 norm. So therefore, this means that e to the 4u is actually a little better than the initial L1 you had.
So this is for the u which satisfy the equation.
Yes.
The Uniqueness equation.
Yes.
But for your sequence.
Oh, that's actually the same because it's very, yeah, the equation is actually very similar, so it applies anyway. So it means that if blow-up occurs, then there is a lower threshold for the concentration of conformal volume. Okay, so if you have blow-up, then you should concentrate at least epsilon 0 in conformal volume. Okay, and then you would expect sort of solutions to converge, as for the linear case, to a kind of fundamental solution. And this will be described, I think, also tomorrow by Yan Li for a different equation. Okay, so I'm assuming now general positive coefficients gamma 2 and gamma 3. So the proposition is that if you consider that operator with a right-hand side which is completely degenerate, so a finite sum of Dirac masses, then you can find a sort of Green's function with multipoles, okay? So which has a sort of a principal behavior of a logarithmic type with a coefficient that depends explicitly, so I call alpha, it depends explicitly on the strength of the Dirac masses that you have on the right-hand side. So it's easy to guess these coefficients by a sort of flux condition. And the difference, so which I call W, is something which is sort of milder than the logarithm. It is actually not so hard to prove it. Okay, so you try with an approximate solution. So you have already an idea about how the solution should look like. So near each pole, it should look like a multiple of the log of the distance from the pole. And you have an idea about the constant in front of the logarithm. Okay, so there is an explicit expression. And this alpha is actually negative. So now you consider the conformal metric with conformal factor given by the approximate solution. So geometrically, since the coefficient is negative, so you're sort of blowing up the metric, and depending on the value of alpha, geometrically, this is a manifold which has either conical points or cylindrical ends or conical ends. So this is a bit bad because you start with a nice compact manifold, and now you have this either non-regular or non-compact manifold. But the thing you gain is that if you set up the problem in this new manifold, you can set up the problem so you gain the variational structure. So you can find actually a solution which now has finite energy. And once you have finite energy, then you can prove Morey type estimates for decay of the solution now W along the ends. And if you retranslate that to the compact setting, you get exactly this nice behavior. Okay, so for the P Laplace equation, so if you forget about the bi-Laplace term, then there are now classical results by Sarin and Kishan-Assami and Veron. But in this case, you have lots of more tools because you have a maximum principle, and then the operator is also homogeneous, so which is not the case here. So this profile will be your guess for the limiting behavior of a blowing up sequence of solutions. Okay, but there is an issue because while in the linear case the Green's function was unique, so the equation was linear, in this case it's not clear at all. So if you develop some singular profile, is the profile going to coincide with a fundamental solution we constructed here? So there is actually a uniqueness issue, okay, which we proved for now special values of the coefficients. So this applies to the determinants of the conformal Laplacian. Okay, so in this case, there is work by Alice and Paul. So they use a Bochner identity and this special relation between the coefficients to show that the energy is actually convex if you work in W22. So it means that if you look for an equation of this type, so n of u is that bed operator equal to some, say, smooth f, then you find a unique solution in W22. So it's a convex function, so you have a unique minimum. But the point is that now the singular solution we constructed before is not in W22. So in a sense, you would like to extend this uniqueness property to data that are of measured type, Dirac or maybe more general. Okay, and for second order PDEs, there is a theory for existence and maybe uniqueness of such solutions. So Boccardo and Galloway constructed or derived the general theory by sort of mollifying the right-hand side, if the right-hand side is a measure, and then considering a class of solutions that are obtained as limits with mollified data. And somehow this is a right class to look in when you want to prove some uniqueness property. I also need to introduce some functional space, which was introduced by Ibanez and Sbordone to study, in fact, some Jacobian determinants. So it's something which is sort of close in LP, close to LP, but it's a little weaker. So you consider norms that are a little weaker than LP, and you look at how they diverge when you send epsilon to 0. So you put some sort of positive power of epsilon in front of it, and you require this to be uniformly bounded in epsilon. So this is called the grand LP space. And I'll be interested in Hessians that are in L12. So, and that's actually a space which is a little bigger than the Marcinkiewicz space. Okay, so using some arguments by Ibanez and Ibanez-Greco-Sbordone, so you can show that the singular solution that you constructed before must coincide with all solutions that are in W2, 1, 2, 2 parentheses and which are of mollifiable type. So in a sense, this class of solutions are the ones that can be obtained by passing to a limit along a sequence of solutions with a smooth right-hand side, as for our blowing up solutions. And you can show that actually the profile coincides with the previous one I described. Okay, so with this nonlinear fundamental solution. And actually this uniqueness argument works not only for a linear combination of Dirac masses, but for any measure data on the right-hand side, so provided the measure is finite. Okay, so now an idea about the proof of the theorem. So let me consider a sequence of solutions to these approximate equations. So at each blow-up point, we saw you must accumulate at least epsilon 0 in conformal volume. All right, so you pass to the weak limit of the conformal volume. So you accumulate some, so you're going to form a finite number of Dirac masses with coefficients beta I, no less than epsilon 0. And then there could be possibly some sort of continuous part in this measure. And this continuous part must be the exponential of a possible weak limit of your approximate solutions. Okay, as a first step, so you use a Poljave identity to show that in fact these weights beta I must be no less than 8 pi squared gamma 2. So which is again the integral of the natural curvature on S4. Okay, but then if you get a lower bound on this strength beta in the Dirac delta, so since you know you have uniqueness of fundamental solutions, then you know that the limiting profile of your solutions un must be of this type, so alpha log of mod x. And if beta is equal to 8 pi squared gamma 2, then this constant alpha must be less or equal than minus 2. So which means that the blow-up rate of this singular profile is quite fast. And if the blow-up profile is quite fast, you can prove that actually the continuous part h must be actually 0. Because if you get some sort of continuous limit, then say in a small sphere around the blow-up point, then the volume is bounded from below, but then in the interior it grows very fast, and that will give you divergence of the volume inside a small ball around the blow-up point. But we had uniform bound on the total volume, so the weak limit must actually be 0. Okay, so this function h is 0. But now, somehow, the right-hand side is a pure linear combination of Dirac masses, and then you know exactly what the singular profile looks like, and use the Poljave identity again to quantize exactly the betas here. And then you derive again a contradiction from this non-quantization of the total U curvature. Okay, so this leads via min-max theory to an existence result. So basically we remove the second assumption in Alice and Paul's theorem. So just suppose that the integral of the U curvature is not a multiple of 8 pi squared, then we can find the existence of an extremal metric. It's no more minimal, it would be a saddle type solution. So it's an interesting open problem, I think, to understand the case in which this integral is exactly a multiple of 8 pi squared. So in the previous case, you had some energy with compactness properties, and under this condition, you lose compactness. So typically, the energy has some kind of asymptotes. So you might find, say, a minimizing sequence that diverges along an asymptote. And in that case, it would be important to understand the shape of the asymptotes. So whether it's going this way or whether it's going this way. So the second case is actually more favorable, because if you have an energy with an horizontal asymptote going to, say, a constant from below, when you apply a gradient flow, a negative gradient flow, somehow it pushes back to compact regions in the functional space. So that would be sort of equivalent to understand or define a suitable concept of mass for blown up manifolds via the nonlinear Green function I defined before. Okay, so maybe I'll spend the last minutes talking about the Panitz operator, so the determinant of the Panitz operator. This is actually mentioned in Kahn's book about non-commutative geometry. as a relevant tool for conformal theories in 4D. So the Polyakov action had a role in string theory. And if you want to understand quantum gravity, so there are some models which involve exactly the determinant of the Panitz operator. Okay, analytically, it's also quite interesting. So let me write it down for simple manifolds. So the first one is, say, just a flat torus, no curvature terms. So it's a very clean expression. It has a triple homogeneity, and it's again doubly critical. So the three terms have three different homogeneities, but they scale in the same way. And that's another example on the sphere. So now the curvature is non-zero but constant. So you get some lower order terms and also some exponential term in this expression. In general, it's quite hard to understand this functional, but when they have opposite signs, exactly. And then there are some kind of weird phenomena. So I would say it's a problem almost completely open. And we have just one single result, which is maybe kind of embarrassing from some point of view. But I'll describe it. Okay. So for both the torus and S4, in fact, any constant curvature space, the energy has a local minimum at standard metrics. Okay. But the energy is unbounded from below. So you have a mountain pass structure. And you can see it. So the local minimality was already noticed by Branson, who computed the second variation of the functional. And to check that you have the mountain pass structure, you can use a conformal factor of this type. So epsilon is a small parameter. And geometrically, this is a conformal factor giving you a sort of cigar, so not a bubble. It's like a truncated cylinder. So this sends the energy to minus infinity. But it's just one example because you might have, I mean, you can take any number of cigars and glue them anywhere you like on your torus, on your sphere, and the energy will still go to minus infinity. But differently from the case of Q curvature, you can put as many cigars as you want. So it's not easy to characterize the loss of coercivity as it was done for the Q curvature equation. And OK, so it's the same computation for hyperbolic manifolds. The only thing we were able to prove with Gursky, and that was already some time ago, is that on the sphere, the determinant of the Panitz operator admits a non-trivial axially symmetric second solution, okay, which is not actually the conformal factor of a Möbius action. So this problem, so of course all the Möbius maps will be solutions because the problem is conformal invariant, but this is yet another solution. Okay, and in fact, this is a sort of weird phenomenon because for most geometric problems, the only critical points are actually round metrics. So if you consider spheres, okay, for example, if you impose a constant mean curvature, constant Gaussian curvature, constant scalar curvature, constant Q curvature, and even for the determinant of the conformal Laplacian, there is a unique solution. So that was proved by Gursky. But for this other problem, then there are also non-trivial solutions. So this I just said. In this case, so for the case of the determinant of the Panitz operator, so Branson just computed the second variation of the energy at the round metric. So he saw a sign, and then he speculated uniqueness just from the local second variation. But that's actually not true. So we proved the result just by studying an ODE. It's actually a quite tricky fourth order ODE. So we had to do a lot of analysis, but the technology is really trivial. So it's really via a shooting method. Okay? But you should attack in general, or you might expect to be able to attack the problem variationally. So you have a mountain pass structure, and you really would like to use variational approaches, but we tried very hard, but we always failed. So we don't have any clue about how to control Paris mail sequences or approximate solutions. No idea whatsoever. And you can also find a non-trivial solution on R4 with a much easier equation, because somehow on the sphere there is also an exponential term, but on R4 the equation is kind of homogeneous, so it's much easier to study it. So I conclude just with some open problems. So as I said, our proof for the existence of a second solution is very specific. Okay. So recall that on the torus, the determinant has of the penance operator has this nice simple expression. So it's very hard to control by any means Pallas-Mail sequences. Okay. And this problem is sort of related to another sort of Sobolev type inequality. So by Bochner's identity, the Laplacian squared integrated is equal to the Hessian squared. And in 4 dimensions, so by the Sobolev inequality, you have this quantity which is lower bounded from below. So it's a sort of higher order Sobolev type inequality, and understanding the extremals for this would be useful, I think, to understand also critical points of this energy. But here you cannot, so we have a guess for what the extremal should be. So there is a radial solution we can write down, but there is no symmetrization or a rearrangement technique that works for this case. So that's the Euler equation in R4. So in this, so with no curvature, you can write it down. It's already pretty ugly. You can imagine with curvature what it is. Also, another feature is that okay, the principal term is the bilaplace, and you would expect typically decay of solutions to be logarithmic at infinity, just like the fundamental solution. But in fact, the solutions you find here have inverse quadratic decay. So they are sort of degenerate because they are not only asymptotically biharmonic, but they are asymptotically harmonic. So there is some kind of degeneracy present here. And apart from the compactness issues, there should be some sort of hidden Moser-Thuinger inequality. So I conclude here, and thank you for the attention.